Welcome to WikiPodcast. You know that shimmering heat rising off the road on a summer day? Or those massive plumes of steam you see coming from power plants?
Yeah, or even just the warmth from your car engine after a drive.
Exactly. It turns out all that heat, it isn't just sort of accidental waste.
Mm.
There's a fundamental, unbreakable rule of physics behind it.
A rule that basically says when you're trying to turn heat into motion, you can never, ever get a perfect score. You can't really win with heat.
Perfect efficiency is just
Yeah.
impossible for any machine. Doesn't matter if it's a super advanced Formula One engine or the giant turbines making our electricity.
Or even how our own bodies process energy, actually.
Right. So today we're going on a deep dive into this whole fascinating world of thermodynamics and thermal efficiency.
Yeah, we want to unpack why no engine can ever hit that 100% mark.
Our mission is to explore these universal limits that nature puts on us, look at how different engines try to deal with these built-in losses, and maybe uncover some surprising things about the energy that's all around us.
Get ready to understand the real energy scorecard.
And why even the absolute best machines have this fundamental ceiling they just can't break through.
Okay, so if we're always losing some energy, how do we even, measure how well an engine is doing?
That's where thermal efficiency comes in. Basically, it's a simple ratio. What you get out the useful work versus the total heat energy you put in.
It's a dimensionless number, no units, which makes it super useful for comparing things, like for a car engine, how much fuel energy actually moves the car forward.
Versus how much just turns into heat and, well, disappears into the air.
Exactly. And for something different, like a heat pump, it's about how much heat gets moved compared to the work you needed to move it.
Okay, but here's the big question, the one that's kind of sobering, like you said. Why can't we ever reach 100%?
Well, the first law of thermodynamics, everyone sort of knows that one, right? Energy is conserved. You can't create it or destroy it. Output can't be more than input.
Right. Common sense, almost.
But it's the second law that's the real kicker here. It says that in any real-world process involving heat transfer, the useful output will always be less than the input. Entropy. Think of it as disorder always increases in the universe.
Always.
Always. It means every real-world heat engine, no exceptions, operates somewhere between 0% and, crucially, less than 100% efficiency.
So it's like we're always fighting this uphill battle, always losing some energy somewhere.
Pretty much. And the numbers really drive this home. Let's take a typical gasoline car engine.
Yeah.
Its efficiency is usually around, well, only about 25%.
25%. Seriously. That means, wow, 75% of the energy in the gasoline is just lost, mostly as heat.
Mostly as heat, just dissipated. Think about that. Multiplied by billions of cars worldwide. It's a huge amount of wasted energy, a massive challenge.
It really puts things into perspective, and it's not just cars, right?
Oh, definitely not. Big coal-fired power plants, the ones generating a lot of our electricity, they peak at maybe 46% efficiency.
Still less than half.
Yep. Even those incredibly advanced Formula One power units, pinnacle of engineering, they only manage about 45–50%.
Wow. So even with all that tech?
They're still bumping up against these limits. The largest, most efficient diesel engine in the world hits about 51.7%. And combined cycle power plants, which are pretty sophisticated.
They combine different cycles to squeeze more out.
Exactly. They can get close to 60%.
Yeah.
But even then, look at the energy that's still being lost. It's immense.
So what's actually causing these losses? Why can't we capture more?
You can break it down into three main reasons. First, there's that absolute theoretical limit we talked about,
Yeah.
set by the laws of physics themselves. Think of it as a universal speed limit for efficiency.
Okay. An unavoidable ceiling.
Second, the engine cycles we actually design and use in the real world, they're inherently irreversible. They can't be perfect ideal processes like the theoretical ones.
Right. Theory versus practice.
And third, you've just got the messy reality of actual machines. Friction, heat leaking out, fuel not burning perfectly, all those practical things that chip away at the performance.
Okay, so given all those real-world problems, let's go back to that theoretical limit. What is the absolute best an engine could possibly do? Even in a perfect imaginary world with no friction. Is there a number for that ceiling?
There is. And that brings us to what's called the Carnot efficiency. It's named after Sadi Carnot, a French physicist.
Carnot efficiency.
The second law tells us this is the fundamental upper limit for any heat engine operating between two specific temperatures.
And these temperatures are key.
Absolutely critical. You need the high temperature, let's call it TH, where the heat actually enters the engine system. Think of the temperature right after fuel combustion.
Okay, the hot part.
And you need the low temperature, TC, which is the temperature of the surroundings where the engine dumps its waste heat, like the ambient air or maybe a cooling lake for a power plant.
The cold part where the waste goes.
Exactly. And crucially, you have to measure these temperatures on an absolute scale, like Kelvin, not Celsius or Fahrenheit.
Kelvin. Got it. So can we put some numbers on that, like for the car engine again?
Sure. Let's say the gasoline burns at around 816 degrees Celsius. In Kelvin, that's about 1089 K.
Okay.
And let's say the ambient air temperature, TC, is a pleasant 21 degrees Celsius, which is 294 Kelvin.
Right.
The maximum possible theoretical efficiency, the Carnot efficiency, for an engine running between those two temperatures is calculated as 1 minus TC divided by TH.
So 1 minus 294 divided by 1089.
Which comes out to about 0.73 or 73.0%.
73%. But wait, that's the theoretical maximum.
That's the absolute ceiling.
Yeah.
Even if you built a completely perfect frictionless engine operating between those temperatures, it could never convert more than 73% of the heat energy into useful work.
Wow. So our real-world 25% efficient car engine is not only dealing with friction and heat leaks, but it's also starting from a point that's already way below 100%.
Precisely. It highlights just how much of a constraint this fundamental limit is.
So how could you even improve that theoretical limit, that 73%?
Well, looking at the formula, 1 minus TCTH, the only way to make that number bigger, to increase the efficiency, is to either lower TC, the cold temperature.
Which is hard. That's usually just the environment.
Right. Or you have to increase TH, the high temperature. Make the engine run hotter.
Okay. So that's why engineers are always trying to develop materials that can withstand higher temperatures.
Exactly. That's a huge driver in material science research for engines and power plants. Pushing TH higher directly increases the theoretical potential efficiency. But of course, making things run hotter brings all sorts of other challenges with materials, safety, cost.
It's always a trade-off.
Always. Oh, and there's an interesting side note here about things like fuel cells.
Yeah, what about them?
Since fuel cells convert chemical energy directly into electricity without going through a heat-to-work conversion cycle like an engine, they aren't actually bound by the Carnot efficiency limit in the same way.
So they can theoretically be more efficient than that Carnot limit.
Theoretically, yes, because they operate on a different principle entirely. They bypass that specific thermodynamic bottleneck of heat engines.
Fascinating. Okay, so we have the Carnot limit as the absolute ceiling, but you mentioned real engine cycles are inherently less efficient anyway because they're irreversible.
Right. The Carnot cycle itself is a purely theoretical, ideal, reversible cycle. Real engine cycles, the ones we actually build, involve processes that inherently generate entropy. Things happen too fast, there's friction, heat transfer across finite temperature differences, all sorts of irreversibilities.
But it's the design of the cycle itself matters a lot.
Hugely. The way heat is added to the working fluid, how it's expanded, how heat is removed, it all impacts the actual efficiency you can get, even before you account for mechanical losses.
So let's talk about some of those common cycles, like the one in my gasoline car.
That's the Otto cycle, named after Nicholas Otto. It's what powers most gasoline engines, and potentially hydrogen combustion engines, too. Its theoretical efficiency depends quite strongly on the engine's compression ratio.
Compression ratio, how much the air-fuel mixture is squeezed before ignition.
Exactly. Generally, a higher compression ratio leads to higher potential efficiency because you get a bigger temperature rise during combustion and more effective expansion.
But there's a limit, right? You can't just keep compressing indefinitely.
Correct. Compress it too much in a gasoline engine, and the fuel mixture can auto-ignite uncontrollably before the spark plug fires. That's engine knocking or pinging, and it's bad for the engine and efficiency.
So there's a practical ceiling on compression for auto engines.
Yes. Ideally, modern auto cycle efficiencies might reach between, say, 56% and 61%, theoretically. But again, the real-world number, like I said, drops significantly due to all those other losses.
Okay, what about diesel engines then? They're in trucks and trains.
Right. They use the diesel cycle, named after Rudolf Diesel. The key difference is how ignition happens. There's no spark plug. Air is compressed so much that it gets incredibly hot.
Hot enough to ignite the fuel just by injecting it?
Precisely. Fuel is injected right at the point of maximum compression, and it ignites spontaneously. Now, interestingly, if you compare an Otto cycle and a diesel cycle at the exact same compression ratio, the Otto cycle is actually slightly more efficient theoretically.
Oh, really? But I thought diesels were more efficient.
They generally are, in practice, often 30–35% more efficient than comparable gasoline engines. And the reason is, they can use much higher compression ratios.
Because they don't have the knocking problem since fuel isn't added until the last second?
You got it. Since they only compress air, They can use compression ratios maybe twice as high as a gasoline engine without risking knocking. And that higher compression ratio more than makes up for the slightly less efficient cycle shape, leading to better overall real-world efficiency. That's why they're great for heavy-duty stuff where efficiency really counts.
Makes sense. What about the big power plants? You mentioned steam.
That's typically the Rankine cycle. This is the workhorse for generating most of the world's electricity, whether it's from coal, nuclear, natural gas, or even solar thermal. It involves phase changes, heating water to create high-pressure steam, expanding that steam through a turbine to generate power, condensing the steam back into water, and pumping it back to start again.
Water turning to steam and back again?
Pretty much. Modern steam turbine plants, maybe using reheat stages to improve things, can hit around 47% efficiency.
Okay. And you mentioned combined cycles getting close to 60%.
Right. That's where you take something like a gas turbine, which runs on a different cycle we'll get to, and use its hot exhaust gases, which would otherwise be waste heat, to boil water and run a Rankine steam cycle. You're essentially getting a second bite at the energy apple.
Very clever, stacking the cycles.
It's a really effective way to boost overall efficiency.
So what's that gas turbine cycle? You mentioned jets.
That's the Brayton cycle. It's the basis for gas turbines used in power generation and famously for jet engines. It involves continuously drawing in air, compressing it, mixing it with fuel, and burning it in a combustion chamber, and then expanding those hot, high-pressure gases through a turbine.
And in a jet engine, that expansion provides thrust.
Exactly. Or, in a power plant, the turbine drives a generator. The efficiency of a simple Brayton cycle depends a lot on the pressure ratio, how much the air is compressed, and the maximum temperature the turbine blades can handle.
Again, pushing those temperature limits.
Always. Higher pressure ratios and higher turbine inlet temperatures generally mean better Brayton cycle efficiency, but that requires very advanced engineering and materials.
So we've got the fundamental Carnot limit, then the limits of the specific cycle designs like Otto, Diesel, Rankine, Brayton. But then you said there's a third layer of losses, the messy real-world stuff.
Absolutely. Even with the best possible cycle design operating below the Carnot limit, real machines bleed efficiency in so many ways. It's like death by 1,000 cuts.
Give me some examples. What are these practical gremlins?
Well, friction is a big one. Pistons sliding in cylinders, gears turning, bearings spinning. All that mechanical rubbing creates heat instead of useful work.
Just wasted heat from parts moving.
Yep. Then there's incomplete combustion. Sometimes not all the fuel molecules manage to burn completely, so you don't get all their chemical energy released. You get unburned hydrocarbons or carbon monoxide in the exhaust.
Wasted fuel, basically.
Exactly. Heat loss is another major one. The combustion chamber is incredibly hot, and some of that heat just radiates or conducts away through the engine block before it has a chance to push the piston or turn the turbine.
Escaped heat.
Right. You've also got things like aerodynamic drag inside the engine, just the energy it takes to push air through the intake, past valves, and out the exhaust.
Even moving the air costs energy.
It does. And then there's the energy needed to run auxiliary systems, the oil pump, the water pump for cooling, the alternator. They all draw power from the engine's output. And even things like imperfect valve timing. If the intake and exhaust valves don't open and close at the absolute perfect moments, you can lose efficiency in how the engine breathes. All these things add up.
Wow, it really is a battle on multiple fronts just to get that, 25% or 40% efficiency. It's amazing they work as well as they do, in a way.
It really is a testament to decades of engineering refinement trying to minimize all those practical losses.
So switching gears slightly, we've focused on engines making things move. What about devices that just, make heat, like an electric heater or a furnace? How does efficiency work there?
That's simpler in concept. For those, thermal efficiency is just the ratio of the useful heat output you get divided by the total energy input.
So if my furnace burns gas with 300 kilowatts of energy content and delivers 210 kilowatts of heat to my house ducts.
Then it's 210 divided by 300, which is 0.7 or 70% efficient. The other 30% is going up the chimney as hot exhaust gases or radiating from the furnace itself.
Okay, that makes sense. What about something like an electric space heater, the kind with glowing wires?
Electric resistance heaters are interesting. They are actually very close to 100% efficient at converting electrical energy directly into heat within the space they are heating. Pretty much all the electricity consumed becomes heat.
So they're perfectly efficient.
At turning electricity into heat, yes.
Mm-hmm.
But you have to consider the efficiency of generating that electricity in the first place, which likely involves a power plant running at, say, 40–60% efficiency, plus losses in transmission lines. So the overall system efficiency might be much lower.
Right. Got to look at the whole picture. Okay, now for the really mind-bending part. Heat pumps and refrigerators. You said they work differently.
They do. They are essentially heat engines running in reverse. Instead of using a temperature difference to produce work, they use work usually from electricity running a compressor to move heat from a colder area to a warmer area.
Moving heat against its natural flow from cold to hot.
Exactly. A refrigerator moves heat from inside the cold box to the warmer room air. A heat pump, in heating mode, moves heat from the cold outside air or ground into your warmer house.
And you said they don't use efficiency, they use COP.
Right, coefficient of performance or COP. And here's why. Because they are moving heat rather than converting primary energy into heat, they can actually move more heat energy than the amount of work energy you put in to run them.
Wait, more energy out than in? Doesn't that violate the first law?
It sounds like it, but no. It's not creating energy. It's just pumping existing heat energy from the cold source, like outside air, to the hot destination, your house.
Yeah.
The electrical work you put in is used to facilitate this pumping action. So the total heat delivered to the hot side is the heat extracted from the cold side plus the work energy you put in.
Ah, okay. So the COP can be greater than 1 or greater than 100%.
Definitely. A typical air source heat pump might have a COP of, say, 3 or 4 in moderate conditions. That means for every 1 kilowatt hour of electricity it uses, it delivers 3 or 4 kilowatt hours of heat to your house.
That's amazing. Compared to an electric resistance heater with a COP of 1?
Exactly. That's why heat pumps can be a much more energy-efficient way to heat a home than direct electric heating, or sometimes even burning fossil fuels directly in a furnace, depending on the furnace efficiency and electricity source.
Are these COPs limited too, like engine efficiency? Is there a Carnot limit for them?
Yes, there is. Carnot's theorem also applies to refrigerators and heat pumps, defining the maximum possible COP between two given temperatures, TH and TC. The ideal COP depends on those absolute temperatures.
And is there a difference between cooling and heating?
Yes. Interestingly, for the same device operating between the same two temperatures, the ideal COP for heating is always exactly one higher than the ideal COP for cooling refrigeration.
Why is that?
Because when you're heating, the work energy you put into the system also ends up as useful heat in the warm space, adding to the heat pump from the cold side. When you're cooling, that work energy still turns into heat, but it's released on the hot side, outside the fridge, which isn't the desired effect, so it doesn't count towards the cooling COP.
Clever. Okay, one last thing you mentioned, this heating value stuff. HHV and LHV?
All right, this is really important when you see efficiency figures quoted for anything that burns fuel, like engines or furnaces. Fuels containing hydrogen, like natural gas or gasoline, produce water vapor when they burn.
H2O, yeah.
Now, if that water vapor leaves as steam in the exhaust, it carries away a certain amount of energy, the energy it took to turn it into vapor, latent heat of vaporization. The lower heating value, or LHV, measures the heat released, assuming that water stays as vapor and its latent heat is lost.
Okay.
The higher heating value, or HHV, measures the heat released, assuming that water vapor condenses back into liquid water within the system, releasing that latent heat as well. So HHV is always higher than LHV for the same fuel.
So if someone quotes an engine efficiency, say 40%, but doesn't say if it's based on HHV or LHV.
It could be misleading. An efficiency based on LHV will always look better, numerically higher, than one based on HHV for the same engine performance, because the LHV input value is smaller. So, for a fair comparison, you always need to know which heating value is being used. High-efficiency condensing furnaces, for example, are specifically designed to capture that latent heat, so their efficiencies are often quoted based on HHV.
Good to know. Always check the fine print on efficiency numbers.
Yeah, boy.
So wrapping this all up, what's the big picture here?
Well, it really comes down to the second law of thermodynamics. It puts a hard, unavoidable limit on how much useful work we can ever get from heat. No matter how smart our engineering gets, some heat loss, some inefficiency, is baked into the laws of the universe for heat engines.
A fundamental ceiling we can approach, maybe get closer to, but never actually reach 100%.
Exactly. And understanding that isn't just academic. It shapes our entire energy landscape, the design of cars, power plants, heating systems, everything.
And it's the driving force behind so much innovation, right? Trying to push closer to those limits with better materials, smarter cycles, finding ways to recycle waste heat.
Absolutely. It's a constant push to minimize that unavoidable waste, driven by the need for better performance, lower costs, and increasingly environmental concerns. Even small percentage point gains in efficiency, scaled up globally, can mean huge energy savings.
So, thinking about all of this, Considering these fundamental limits on engine efficiency, what everyday technology do you think wastes the most heat? And how might understanding these limits change your approach to energy use?
That's a great question to ponder.
Thanks for listening. Write us your opinion on this question in the comments. Subscribe to the channel to help more listeners reach our episodes. Thank you, and have an amazing day.